Hello everyone, my name is Bharti Patel, Assistant Professor, Computer Science and Engineering Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today, let's do a quick recap of the key concepts we covered in our previous lecture on 3D image visualization and manipulation. 3D image visualization involves the depiction of objects or scenes with depth, height and width, creating a more immersive experience than 2D images. This is achieved through rendering techniques that simulate lighting, shading and other effects. 3D images can be viewed using devices like VR handsets, adding fields like gaming, architecture and medical imaging. On the other hand, 3D image manipulation encompasses the creation, editing and animation of 3D models. These models, often textured and mapped, can be animated through keyframes and physics simulations and integrated into various applications. This technology has transformed industries, enabling realistic experiences and facilitating intricate design and analysis tasks. So let's begin with the detailed understanding of the today's lecture on 3D image filtering and segmentation. So brief overview of 3D image processing is here. 3D image processing is the manipulation and analysis of images with depth, width and height dimension. Unlike traditional 2D images, 3D images offer a richer representation of objects and scenes. This dimensionality unlocks new opportunities for applications in fields such as medicine, entertainment, manufacturing and more. So there are some significance of 3D image processing. 3D image processing holds immense significance due to its ability to capture and convey spatial information. Some key points are here, like first one is enhanced realism. Adding depth to visual data results in more immersive and lifelike experiences, benefiting fields like virtual reality and gaming. Next one is accurate analysis. In this, precise measurements and detailed analysis of volumetric data are crucial in areas such as medical diagnosis, material science and geological exploration. Then the next one is medical advancements. 3D processing facilitates advanced medical imaging, aiding surgeons in preoperative planning and diagnosis. So the next one is innovation in industry. In this, it includes manufacturing and design industries benefit from 3D processing for quality control, prototyping and reverse engineering. So specialized techniques for filtering and segmentation are here. While 2D image processing techniques are well established, 3D images present unique challenges that necessitate specialized opportunities. These challenges include, first one is increased complexity. In this, 3D data introduces an additional dimension requiring adjustments to algorithms and techniques. Second is varying intensity and texture. In 3D images, intensity and texture variations can be more pronounced, requiring adaptive and robust filtering and segmentation methods. Then the next is spatial relationships. Spatial relationships between voxels, that is called 3D pixels, become crucial in filtering and segmentation, demanding methods that account for neighborhood interactions. So, using Python for 3D image processing is here. Python offers powerful libraries and tools for 3D image processing, making it an excellent choice for researchers and practitioners. Libraries like NumPy, SciPy, OpenCV and specialized packages like SimpleITK and PIDCOM enable efficient manipulation and segmentation of 3D images. So, what is the image filtering and its purposes in 3D context? We have to learn. Image filtering is a fundamental technique used to modify or enhance an image by applying a filter or kernel. In the context of 3D images, filtering serves to improve image quality, reduce noise, highlights features, or prepare data for further analysis. It involves altering pixel values based on their neighbors' values to achieve desired effect. So next is convolution and its role in applying filters to 3D images. So convolution is a mathematical operation that forms the core of image filtering. In 3D image processing, convolution involves sliding a filter over the image's voxel grid. At each position, the filter's values are multiplied with the corresponding voxel values, and the results are summed to determine the new value of the central voxel. This process is repeated for every voxel, effectively applying the filter to the entire 3D image. So, some examples are there for 3D filters and their effects. First is Gaussian filter. The Gaussian filter is used for blurring and noise reduction. It assigns higher weights to central voxel and decreases weights for surrounding voxels, resulting in a smoothing effect. So here is the Python code. This is the short description of that Gaussian filter. The code in this, we have to import the library, then the filter called as Gaussian filter is used for input image to identify that particular object, or we can segment that object. So next is median filter. The median filter is effective in reducing salt and pepper noise. It replaces each voxel value with the median value of its neighborhood, reducing the impact of outlier noise. So Python code for this is here. In this, import the library and then define that median filter as a keyword, and with the function here we are giving the input value with size equal to 3, which is predefined. Then next is age detection filter, and the most common example is Sobel, or the another example like Kenny is also one of the type. So here in age detection, it filters highlight edges and gradients in an image. They emphasize rapid intensity changes and are essential for object boundary detection. So Python code for this particular filter is here with the library packages and with that particular name called as Sobel. Here we are taking as an example for age detection filter, and in this function we are giving the input image value. So next is anisotropic diffusion filter. This filter is used for noise reduction while preserving edges. It diffuses noise along edges while preventing excessive blurring. So Python code for this particular filter is here. Here we are taking sky image as a library function and we are importing that anisotropic diffusion. After that, we are taking a function as anisotropic diffusion with the input image value, and it is decided as 10. Through the application of these common 3D filters in Python, we can achieve various image enhancement and noise reduction effects, highlighting the power and versatility of image filtering techniques in the context of 3D images. So next topic is 3D image filtering techniques with the detailed description. So overview of advanced 3D filtering techniques such as anisotropic diffusion, bilateral filtering and non-local means. We have to learn all these methods. After that we have to learn visual examples which will show that how these techniques preserves the edges and details in 3D images. So one by one we have to learn. First we have to start with the overview of advanced 3D filtering techniques. So advanced 3D filtering techniques offer more sophisticated ways to enhance images while preserving important features. Some key techniques include: first is anisotropic diffusion. It is selectively smooths on image and preserving edges and boundaries. It diffuses intensity changes across neighboring voxels while preventing excessive smoothing along edges. Next is bilateral filter. Bilateral filtering considers both spatial and intensity differences. It smooths an image while preserving edges by adjusting filtering based on similarity between voxels. Next is non-local means filtering. Basically, this filter reduces noise while preserving fine structures. It compares similarities between patches of pixels to determine filtering weights, making it effective for complex textures. So, visual examples which is going to illustrate how these advanced 3D filtering techniques maintain edges and details in 3D images. So, examples are here. For anisotropic diffusion, we have to import the library, then we have to use the function with that name it is defined here and define the input size with the weight value. Example for bilateral filtering, this is the code. We have to import the library, then we have to choose the function and we have to define all the values like sigma spatial value and sigma range value. Next is non-local mean filtering. This is the code for this particular filtering method. We have to define the libraries. After that, we have to define the name with the input image and the value. By showing these advanced 3D filtering techniques with visual examples and corresponding Python implementations, we emphasize their effectiveness in retaining crucial image attributes while improving image quality. So, next is 3D image segmentation. Complexities in segmentation of 3D images are here. Segmentation of 3D images presents unique challenges owing to factors like first one is noise and artifacts. In this we have to discuss that how noise from acquisition or imaging modalities can disrupt segmentation accuracy. Then we have to emphasize the need for robust methods that can differentiate between noise and meaningful structures. Then the next one is varying intensity and textures. In this we have to learn that how different regions in 3D images can exhibit varying intensity and texture. Then the next one is mention the challenges of identifying consistent features for accurate segmentation. So the next one is object complexity. In this we have to highlight that how 3D objects can have complex shapes and structures. After that, how this complexity can hinder conventional segmentation algorithms. So starting with the introduction to region based segmentation and boundary based segmentation. Two fundamental approaches for 3D image segmentation are called as region based and boundary based. In region based segmentation, we have to study that how region based segmentation groups voxels into coherent regions based on intensity, texture or other attributes, and mention that this approach is suitable for identifying objects with consistent internal properties. In boundary based segmentation, we have to learn that how boundary based segmentation focuses on detecting edges or boundaries between different regions and highlight its effectiveness in segmentation objects with distinct boundaries or surfaces. So example for region based segmentation is here. We have to import the library function and use that function name called as segments with the value. And here is the example for boundary based segmentation. We have to import the library function and here we are using Sobel, as we told in previous lecture also that Sobel is a very important example for boundary detection. So by addressing the challenges in 3D image segmentation and introducing both region based and boundary based segmentation approaches along with corresponding Python implementations, we gain insights into strategies for tackling segmentation complexities in the context of 3D images. So in detail, we'll see region-based segmentation method. Here we have to learn the region growing and watershed segmentation algorithm and pros and cons of each method with visual examples. So region growing is a region-based segmentation technique that starts with seed points and iteratively expands regions by adding neighboring pixels that meet predefined criteria, such as similarity in intensity or texture. The process continues until no more pixels can be added. So watershed, that is the next one. So watershed segmentation is a region-based technique inspired by hydrology. It treats intensity value as a topographic relief and simulates flooding. The image is treated as a landscape and regions from where the flooding waters meet. So some of the pros and cons of region growing segmentation is here. Pros like intuitive, it is easy to understand and implement. It can handle irregular shapes. It is suitable for objects with consistent internal properties, and some cons is like sensitive to seed point selection, and it can be sensitive to noise and varying intensities. It may result in over or under segmentation. Some pros and cons of watershed segmentation is here. Pros like it can handle complex and irregular shapes. It is useful for segmenting, touching or overlapping objects. It provides distinct boundaries, and some cons are there like prone to over segmentation and sensitive to noise, and it requires preprocessing to define markers. So Python implementation is here. For that segmentation techniques, we have to analyze for region growing segmentation. By this code, here we are taking the library function and using that particular segmented image with the function name and input image and seed value. Then example for watershed segmentation. Here is the library function and again taking the function with the input image and markers. So by explaining and contrasting the region growing and watershed segmentation methods accompanied by visual examples and Python code, we gain a comprehensive understanding of these region-based techniques and their strength and limitations in 3D image segmentation. So next is boundary-based segmentation method. In this we have to learn the age detection technique in 3D, including gradient-based and multi-scale method, and the comparative example that illustrate that how these methods identify object boundaries. So starting with that age detection techniques. So age detection is a boundary based segmentation technique that identifies abrupt intensity changes in an image representing object boundaries. Two key categories of age detection methods in 3D are. For that we have to learn first gradient based age detection example, and here is the example. In this we have to include the input image with distinct object that highlights the result of applying a gradient based age detection algorithm. Next one is multi-scale age detection example. In this different image with various objects at different scales are present that illustrate the outcomes of a multi-scale age detection method that emphasizing its ability to capture ages of different sizes. So Python implementation is here for gradient based age detection Sobel operator, and this is the code you have to learn your system and get the output. After that example for multi-scale age detection, that is called Kenny age detector, and the code is here. Again you have to take this code and learn and get the output. So by introducing and contrasting gradient based and multi-scale age detection methods accompanied by visual example and Python code, we gain insights into these boundary based segmentation techniques and their applicability in detecting object boundaries with 3D images. So some advanced segmentation techniques are also there. We have to learn with more sophisticated methods like graph cut segmentation and active contour. We have to learn the suitability for complex structures and anatomical objects. So here is the brief overview of graph cut segmentation. Graph cut segmentation is an advanced technique that models image segmentation as a graph optimizer problem. It divides an image into regions by contrasting a graph where nodes represent image elements and edges represent interaction between elements. The graph is then partitioned to minimize the energy, resulting in segmentations. So here is the brief overview of active contours in 3D. Active contours, also known as snakes, are deformable models that iteratively adjust their shape to fit the object boundaries. In 3D, active contour can evolve within volumetric data to accurately delineate complex anatomical structures. So, suitability for complex structures and anatomical objects. Both the method called as graph cut segmentation and active contours are well suited for segmenting complex structure and anatomical objects in 3D images. Start with the graph cut segmentation. In this we have to discuss that how it excel in segmenting object with irregular shape and complex interaction, and that mention its application in medical imaging for organ segmentation and cell tracking. Then next is active contours. In this we have to learn that how active contours are effective in segmenting anatomical structure with varying shapes and topologies, and emphasize their utility in medical imaging for organ and vessel extracting. So here is the example for graph cut segmentation, and first of all we have to import the library, then we have to take the image which we are going to implement and then assign all the values. Here is the example for active contours, and we have to import the library and take the function. In this function we have to take the input images and we have to initialize all the values like alpha, beta and gamma. So by providing an overview of graph cut segmentation and active contours in 3D along with their suitability for complex structures and anatomical objects supplemented with Python code examples, we gain insight into the capabilities of these advanced segmentation techniques in the realm of 3D image analysis. So another topic which is called applications of 3D image filtering and segmentation. So some of the areas, like first one is medical imaging, here in MRI and CT. So Python code is here. Then the next one is medical science, which display an image of a material sample as well as describing how 3D image processing helps analyze material microstructures, porosity and defects. So this is the code for material science. After that, geological exploration. In this present a geological sample image and how 3D filtering and segmentation aid in identifying rock formations, mineral distribution and geological features. So this is the code. Next one is biomedical research application, which show an image for cellular structure or tissues and discussing that how 3D filtering and segmentation contribute to cell counting, morphology analysis and study biological processes. So this is the code for this biomedical research. After that, manufacturing and quality control. In this it displays objects which are captured and 3D filtering assess in detecting detection, dimensional analysis and quality assurance, and this is the code for segmenting that particular object. After that, entertainment and animation. In this it defines that how 3D image processing enhances visual effects, character animation and game development, and this is the Python code for that particular application. So by illustrating these real world applications of 3D image filtering and segmentation with specific examples and Python code, we emphasize the versatile impact of these techniques across various fields and industries. So future trends and conclusion. Emerging trends in 3D image filtering and segmentation is here. As technology evolves, several emerging trends are shaping the future of 3D image filtering and segmentation. First is machine learning and deep learning. Machine learning and deep learning techniques are being integrated into 3D image processing with potentially automated feature extraction, improved accuracy and reduced manual intervention. This is the code which is defining the use of machine learning and deep learning model with the segmented image. Next is generative adversarial network, which is very commonly used, and it is for data augmentation, denoising and even generating realistic 3D images. Their potential in enhancing training dataset and improving segmentation results, and this is the code which is giving a GAN model. Then next is transfer learning and pre-trained models. Nowadays it is very useful for real world dataset. So transfer learning allows pre-trained model for specific tasks. Its potential for accelerating research and development of 3D image segmentation models, it is very high. So this is the Python code for the transfer learning pre-trained model. So conclusion of this particular topic is reflect on the journey through 3D image filtering and segmentation. After that, emphasize how these techniques have transformed various industries and applications, enabling deeper insight and innovative solutions. It highlights the exciting prospect offered by emerging trends, and particularly the integration of machine learning and deep learning approaches, and also encourages the continued exploration and collaboration to drive advancements in 3D image processing. By discussing the promising future trends in 3D image filtering and segmentation, particularly the integration of machine learning and deep learning approaches, and providing relevant Python code examples, we conclude the presentation on a forward-looking note, inspiring further exploration and innovation in this dynamic field. Thank you.